Hi guys, welcome to another tutorial video. And in this video I want us to discuss or talk about the polar form of a complex number, how we can convert a Cartesian form or a rectangular form into a polar form. So let me say that let z be equal to x plus iy. So this it represents a rectangular form. So this is it's a rectangular form or a Cartesian form. So now if you want to express this one, or you want to convert it now into into polar form, how do we go about it? So I'll say so we're going to say we're going to let x be equal to be equal to r cos cos theta. X is representing r cos theta, and y it will just be equal to also r sin sin theta. So now I will write this. I'll say now z it will just be equal to, where there is x I'll put r cos cos theta, plus I, where there is y I'll put r sin sin theta. Then I can do I can factorize by by r. Then I'm going to have something looking like cos theta plus I sin sin theta. So this is what we call a polar form. You have converted a rectangular form into a polar form. So let's try to move on. Let's see what r is, what is cos theta, what is sin theta. So r is just equal to the to the modulus or magnitude of of z. So we can find r by just squaring x and and y and y. Then you find your your r. And then how do we find now the amplitude or the or the argument? How do we find the amplitude or the argument? So simple, we'll just say theta is the amplitude or the argument. It will just be equal to the tan inverse of y over x. Then you found your argument. So we try to move on. Since now we have come to know that a polar form looks something like z is equal to r, then cos then cos theta plus I in sin theta. So and we know that if a polar, this is the polar form, but you can also express a polar form or write a polar form like z can be equal to r less than the argument. This is also correct. So without further ado, before we go into much in detail, I want you to show you some a certain way where you can when you're dealing when you're converting a rectangular form to polar form, when you're dealing with such kind of thing, there is you have to know what we call special angles. And I've come to notice that most of students they have a little bit challenges when it comes to how to know how to get those special angles. So I want to show you a certain way how I like to get those angles. So I'll say that so you can master this. So I'll say that I'll start with 0, 30, 45, 60, and 90. So after I write that, I'll say 1, 2, 3, 4, sorry for that. I'll say I'll start 0. I'll start counting from 0. Then I'll say 1, 2, 3, 4. So after when I do that, I'll make sure that now I divide everything by 2. I'll divide everything by 2, by 2, by 2, by 2, by 2. After dividing everything by 2, I'll make sure that I square the numerator. Square, 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 square. So after I do that, then I'll say I'll just write sine theta here, cos theta there, and tan theta there. So if I said, let me start with sine. So if I start with sine, the square root of 0, we know that is 0. If we divide anything by 0, it will get a what? A 0 there. So if you punch on a calculator sine 0, it must give you a what? A 0. Let's go. A square root of 1. A square root of 1, that will just give us 1. So then I'm going to have here what? Half. From there, there's no square root of 2. I'm just going to have 2 divided by 2. From here, I want there's no square root of 3. I'm just going to have 3 divided by 2. Then there, the square root of 4, 2 divided by 2, that just give me 1. So if I want to write now for cos, I'll just start from the what? From the end part of the sign where there is 1, I'll start, and that will be the beginning of what? Of cos. This will be the beginning of cos, so I'll say 1 there. So if you punch cos 0, it will give you 1. Cos 0, it will give you 1. So I'll say 1 there. Then I'll say the root of 3 divided by 2. Then I'll say the root of 2 divided. So the root of 2 divided by 2. Then I'll say half here. Then I'll say what? A 0. So when you punch cos 90 to give you a 0, when you punch cos 60 to give you half, when you punch cos 45 to give you the root divided the root over 2, the root of 2 over 2. What about tan theta? How do we do with tan theta? So tan theta, we know that tan is just equal to what? Sine theta over what? Cos theta. So if I start to divide this, here I have 0 divided by 1, I'll have a what? A 0. If I divide half divided by half, if I divide it by the root of 3 over 2, I'm going to have something like this. So we are just going to have what? 1 over the root of what? Of 3 there. So again, here we are having it will just give us 1. When we divide here, it will just give us 1. What about here? We're having the root of 3 divided by 2. Then I'm dividing by half, so I'll say it's going to be like this. That is 2, then half. So 2 goes, I'm just going to have the what? The root of 3. Here, it will just give me what? Infinity. It will just give me infinity. So try to master this table. It will help you a lot when it comes to convert rectangular form to polar form, even vice versa. So now let's try to work on some examples. So question 5 from your tutorial sheet, it's saying that express each of the following complex numbers in polar form. So these complex numbers which have been given, they're in what? They're in a rectangular form or Cartesian form. So now let's try to express them into what? Polar form. So let's begin with part 1 there, which is 3 plus 3i. So I'll say I'll let my z be equal to 3 plus what? 3i. Then I'll find my what? My modulus or magnitude. So my r, it will be just equal to the what? Square root of I will say 3 and 3 again there. Like that. So from there, I'm going to have a 9 plus another 9 there. And from there, you're going to have a root of what? 18. Well, we don't have a square root of 18, but we know this can also express in the form of 2 and what? And 9. And we know the root of 9, so this will be 3 and the root of what? 2, just the same as writing like that. So we are saying now that our modulus is just equal to 3 and the root of what? Of 2. So we keep that. So now let us find our argument. We know that our argument, sorry about that. We know that our argument is just equal to the what? To the tan inverse of what? Y divided by what? By x. So we know from this complex number, we know that our y, we know that our x is just equal to what? To 3, because we know that this can also be written in the form of z is equal to x plus iy, like that. So meaning my x is just equal to what? To 3, and my y is also equal to what? To 3. So we are saying that the tan what? The tan inverse of y, my y is what? 3, and my x is what? Is 3 there. So I'm saying theta, or my argument will just be equal to the tan inverse of what? Of 1. So now, so we're saying that our argument is equal to the tan inverse of 1. So what is the tan inverse of 1? So we can go back to the table we did. So if you try to check, let's check. So the tan inverse of 1. So I'll go on tan, then I'll shift where there is 1 there. Then I'll say, what is the tan inverse of 1? So the tan inverse of 1 is just what? 45 there on top. Yes, so the tan inverse of 1 is just what? 45. So our angle here is equal to what? 45 degrees. But before you get this argument or amplitude, you have to test it on the what? On the Cartesian what? On the Cartesian plane, to see if actually this is the what? Is the actual angle. So let's try to do that. So I'll just sketch a Cartesian plane. Then I'll say my x there, my x is equal to what? Positive 3. Where can I find positive 3? Maybe I can find it somewhere there, just an estimation. But what about my y? My y is also equal to positive 3. Where can I find positive 3 in the y-axis? It's just what there. So here, if you see, it's telling us this angle is falling in the first quadrant. So if this angle is falling in the first quadrant, and what is being given here is true, then which means this angle which you have found is also what? Is also true.